Okay, so now we're going to figure out the image location and magnification using what's called the thin lens equation. What's nice about this equation, it works for converging and diverging lenses, as long as you use the sign convention, which I'll show you in a minute. So here's the equation. 1 over s plus 1 over s prime equals 1 over f. So this is the object distance, this is the image distance, and that's the focal length. So that's all there is to it. It's not so bad. All right, and here is here's this convention you have to follow. All right, so this is positive, this is negative. All right, so s, well, we'll always have positive because we're always going to have it to the left of the lens or whatever. So we don't have to worry about negative. Okay. Now s prime, it's positive when it's a real image. So opposite side of a lens from the object. Okay, so this is a positive s prime, right? Because it's a real image. On the other hand, if it's a virtual image, it's on the same side of a lens as the object, and you're going to draw those dotted lines, right? You're going to have to backtrack the outgoing rays. So f, we already talked about this. F, converging lens positive. F, diverging lens negative. The magnification, it's positive if it's upright, negative is when it's inverted. So this is really important. So I would, keep that handy when you're drawing your pictures and when you're doing your math. All righty, so let's do it. Oh, okay, let's do this. All right, so this is the first one we did. So, so you just need a calculator, All right, so we have 1 over s plus 1 over s prime equals 1 over f. Now, what we want to find is s prime. Okay, so therefore, 1 over s prime equals 1 over f minus 1 over s. Well, therefore, flip them, right? So s prime equals 1 over f minus 1 over s to the negative 1 power. You just flip it. Okay, so for this one, the focal length is 10, so we have 1 over 10 centimeters. And s is 25, so minus 1 over 25 centimeters. So you figure that out with your calculator, then you just flip it. And let's see, when I did that, I came up with, mathematically, I came up with 16.7 centimeters. Okay, so, this is what we did before, and this is what we came up with before. So, not bad, right? So mathematically, you get 16.7. When I did it with a graph, I get 17. It's close enough. And then again, you just, now you know the real numbers, right? So now you can plug them in. You'll get something similar to that. So again, if I had a test question, something like this, I would want to get it right. So I would draw the ray tracing, and then I would do the math. And if they agree, then I feel I probably did it right. If they disagree, well, obviously did it wrong. So it's nice having two ways to solve a problem. So, and neither way is all that difficult. So I would just always check. Okay, the next one we did was this. Oh yeah, let's do this one. That was the second one we did. So, once you get this formula, it's kind of boring, don't you think? So we have this formula. So 1 over f is 1 over 5 centimeters minus 1 over s minus 1 over 20. All right? And look, 1/5 minus 1/20th, that's a positive number. Agree? So you do it. And you get 6.7 centimeters. So that's what you get when you do the math. Now let's see what we did when we drew the picture. Not bad. 6.8, using graph paper, trying to be careful. And then you just, use these formulas to get the rest of the information. Okay, let's do this one. This was the hard one because the object was inside the focal length. Remember that one? That was the virtual image, and it was magnified. So let's do that. So 1 over the focal length, 1 over 25, minus 1 over s, minus 1 over 10. Now look at that. Okay, 1 over 25 minus 1 over 10, that's negative, agree? So when you do this, yeah, you get negative. You get minus 16.7 centimeters. Now let's see how we did. Not so great, whatever, you know. So with the ray tracing, minus 16.3, that's not so bad though. And then again, you know, to find the magnifications, you know, you'd use the actual real numbers. And that would be similar, right? They'd be similar. All right, then let's do the diverging. How do you know it's diverging? As soon as you see that minus sign, you know it's a diverging lens. So let's just do it. Same equation, right? Okay, so now 1 over f, but it's negative. So it's negative 1 over 10 centimeters. And then it's minus 1 over s. So s is 25. All right, so what is that? Well, first of all, it's negative 1/10 minus the 25th. That's going to be negative, right? I mean, so you do the math on the calculator, and you get minus 7.1 centimeters. Okay, so notice the s prime again, just like it's negative, so you know it's a virtual image, right? On the same side of a lens as the object. So this is really useful, you know, this is super useful. Okay, so this is what we had when we did it. So it's supposed to be 7.1, 7.3, not bad. Then again, you would use the real numbers, right? And you'd get something similar to this. So that's really all there is to it. Nice way to check your work. Okay, so that's really it for lenses. Now we need to talk about mirrors. And if you understand lenses, mirrors aren't going to be so bad. But, well, anyway, let's see. So let's go over mirrors. Okay. So here, well, first of all, what kind of mirror is it? And there's different names, unfortunately. But this is how I like to, I think of it as a concave. And the reason I think of it as concave is because, you know, it bends like this, right? So it's kind of like a cave. Agree? If you're looking at it, you know, it goes like this, so it's a cave. So concave. Some people call it a converging mirror because all the incoming rays, you know, all the parallel rays, right? They reflect and they converge, right? These reflected outgoing rays, they all converge at a point, right? So this is the focal point. Real rays converge at this point. So it's concave or converging mirror, whatever you want to call it. And this, okay, so there it is. Okay, on the other hand, again, this is where we are, right? We're over here, the object's over here. So this is certainly not a cave. You don't see too many caves. This, from our perspective, this is not a cave, right? And so if it's not a concave, it's a convex. And some people call it a diverging. And that's pretty good because, you know, look at these outgoing rays. They certainly don't converge, right? Here, the outgoing rays converge, you know. But here, they diverge, right? Here they diverge. The outgoing rays diverge. So diverging. Okay, so since they don't converge over here, what are you going to call a focal length? Well, you always backtrack on the outgoing rays to find things. So this is the focal point. Rays appear to diverge from this point, right? Okay, so it's the same kind of thing, right? You buy a mirror and it has a certain focal length, and you know where the object is. What you want to do is find the image. Very, very similar. Now, hey, this is awesome. Look, with the lenses, we had 3 rays you could draw. You only really need 2. Third is a check. Here you have 4 rays. So it's nice, right? And you're going to see something else that's nice. Remember what we had before? We had parallel in, focal out, focal in, parallel out. Well, we kind of have that in a sense, but it's a mirror, you know? So look, here's your object. Parallel in, now it reflects. Focal out. So if you just remember that, parallel in, focal out, you got it. Look at the other one. Focal in, parallel out. Well, that's awesome too, right? Now this one, you can't beat this one. You just start at the height of the object, you just go to the center and back. So this angle here is supposed to equal that angle here. It's kind of hard with the PowerPoint, you know, but whatever, you know. Now this one, this is something that's kind of cool. Sometimes, it depends. So this is supposed to be a spherical mirror. And so if it's a, you know, okay, so if it's a sphere, it's, you know, in 2 dimensions is a circle, right? So this is like a circle, circular arc, and this is the center of the circle. So the center of the circle is twice the focal point, all right? So here's the focal point, then you just double it. So if you're at the center of the circle, you just draw the ray towards the mirror, and it just reflects back on itself. So this is sometimes useful. Depends on how much room you have on your paper, you know. But, I mean, these are great because they're very similar to what we've done before. This is always a good one, right? You know, this may or may not be helpful. Okay, so that's that. And the convex is kind of a pain, I admit it. But what are you going to do? But again, it's similar though, right? Okay, now that's kind of a messy diagram, I admit, but just deal with it. So, but 4 rays again, all you really need are 2, but I would suggest you do the third just as a check. But it's similar to what we did before. Watch. Here's the object. Parallel in. Now come on, it's going to diverge, right? So it diverges. So what do? You backtrack. Focal out. Isn't that nice? Parallel in, diverges, focal out. Great. Okay, let's do number 2. Okay, number 2 is focal in, right? So you aim this thing at the focal point, but it's a mirror. So focal in, parallel out, right? So this is the focal in, but it reflects, so it goes parallel out. So that's number 2. So these 2 guys are number 2. Number 3, again, it's useful if you have a big piece of paper. So that's the focal point, so you double it, you get the center of the circle, and you just go straight, right? Just straight. Can't beat that. And then number 4 is the nice one too, right? You just start here, you go here, and then that. So again, it doesn't look it on the slide, but this angle is supposed to equal that angle, right? The law of reflection. So there you go. All right, so that's that. Okay, and guess what? All right, so that's the ray tracing. So here's the math. Same equation. I mean, how much better can it get? Same equation. But now we got to add a little bit to this important table. All right. So okay, so let's see. S prime. S prime is positive, right? Real image in front of the mirror. Okay. So for mirrors, S prime is positive when the image is in front of the mirror. It's negative when the image is behind the mirror. Okay. The focal point is positive for converging or concave mirror. Focal point is negative for diverging lens or diverging mirror, or what I would call a convex mirror. Okay? And then it's all the rest of it. So it's nice, right? There's so many similarities here. You don't have to memorize a gazillion things. All right, so let's do it. All right, let's do it. So actually, you should be able to do this now. So please pause your video and draw the ray tracing for this. All right, so make sure you do it. And while you're doing that, well, let's see. So you draw that right now, please. Okay, I'm not going to draw. I'm just going to show you the answer. Okay, so, all right. So these are kind of a pain. I mean, sorry, but they are, right? So, because you really got to, play around with where you're going to draw everything on your paper, because you don't know if the image is going to be on the behind the mirror, in front of the mirror, before you get used to it. All right, so here's the mirror, and here's, let's see, S is 40. So this is 40. And the focal length is 20. So I drew my mirror, I drew my focal point, and I draw my object. All right, ready? So here we go. Parallel in, it reflects, focal out. All right, next one, focal in, parallel out. Well, we're done, but let's just keep going, right? I also like to draw number 4 as a check. Number 4, you just go to the center here and you reflect. Bingo. Oh, well, isn't that something? Right, so S prime is the same distance as S. So they're both equal to 40 centimeters. And what's the magnification? Well, it's 1. Well, it's -1 actually, right? It's -1. Agree? Because it's minus S prime over S. And you can see it's inverted. Okay? Okay, now what I'd like you to do, please, is pause your video and do the math. So pause your video and do the math for this. Oops. Yeah, let's see. So do that. Okay, I assume you've done it. So 1 over S plus 1 over S prime equals 1 over F. So therefore, we want to get S prime. So 1 over S prime equals 1 over F minus 1 over S. So therefore, you flip both sides. So you get S prime equals 1 over F minus 1 over S to the -1 power. All right. Okay, so we have 1, what's the focal length? 20. 1 over 40. Okay, 1 over 20 is bigger than 1 over 40, so it's going to be positive. So you flip it, and you get, well, you just do it in your head, right? I mean, get common denominators, right? So we have 2 over 40 minus 1 over 40, that's 1 over 40, so I flip it, you get 40. There. Okay. So there you go. All right. So there's the math. I did the math and everything, and the magnification minus S prime over S, so it's -1, which you already know that. Okay, let's do another one. I mean, we got to do a convex, right? So let's do the convex. And notice there's a minus sign. But again, just to warn you, they might say it's in front of a convex mirror with a focal length whose with magnitude 20. So you have to put in that minus sign. It's kind of rotten, but they do it, you know? Okay, so here we go. So here's the convex mirror. Okay, let's see. S is 30, so scale drawing 30. Focal is 20, all right? So once again, parallel in, it diverges, but this focal out, you backtrack, it goes through the focal length. I didn't do number 2. Oh, this time I did the center, right? So there's so this is the focal length, so I doubled it to get to the center. It's always an easy one, you know? Just go from here to the center of the circle, and then I always go number 4, right? Number 4, in and out. So this angle equals that angle. So again, you look at the outgoing ray. So here's the outgoing ray. Where's the other one? Here's the outgoing ray right here. And here's the other one right here, right? Okay, so there it is. Now again, this is a mirror, right? So this is not real light, you know. It just backtrack the real light rays. So it's a virtual image. It's a virtual image. It's behind the mirror, so we have to give that minus sign. And, right, behind the S prime, negative, virtual, behind the mirror. And then the math is, you know, just plug and chug, right? The focal length is -20, S is 30. You just plug it in, you get -12. Hey, we did pretty, that's what sort of kind of we got, right? Then you just plug it in the formula. So that's really all there is to it. All right. All right, so I promise you'll have problems like those on your homework and on your test, and also in lab. So you want to make sure you know how to do these drawings and do your math. Make sure you know how to do this math with your calculator. That's what people have more problems in. They just don't know how to use their calculator to do this. So make sure you know how to do that. Okay, we want to end up by talking about, let's kind of look at the last chapter and this chapter. So the last chapter was the wave model of light. This chapter was the ray model of light. So the question is, which one do you use? I mean, you know, under what circumstances do you use the ray model, and when do you use the wave model? Now remember, a ray just keeps going straight, right? But what happens to a wave? Well, what did we learn about if you shoot a laser through a single slit? It bends, correct? All right, so basically if it goes straight, ray. If it bends, wave. Well, okay, please be more precise, right? All right, so here's a nice way to think. Yeah, I already said that. Right? Goes through a slit, it bends, so you have to use wave. So here's a really neat way to think of it. So here's a, you know, whatever piece of paper, something like that with a hole in it. And here's the screen, you know, somewhere away. So if you shine light through this, and this, the size of this hole is exactly the same as the size of that hole, that means light's acting like a ray, right? There's no bending. On the other hand, if this is larger than this, that means that the diffraction is important. So you got to use wave. All right, so let's just read this. If light travels in straight lines, the image on the screen is the same size as the hole. Yeah, that makes good sense. Diffraction will not be noticed unless the light spreads over a diameter larger than d. Oh, that's totally awesome. So that makes a lot of good sense. All right, well, I'm still not answering your question, though, right? Or the question. So we gotta get some numbers, you know? Gotta get some numbers. All right, well, you know, by the way, when we talk about like a single slit diffraction, this is the central max. Why are we ignoring the other ones? Because remember, the other max, you know, the secondary maxes, they're really, really, really dim compared to the central one. The photographs in the book, they make it look like they're brighter, but they're really not, okay? But anyway, okay, so this is the central max of a single slit diffraction. Now, earlier, we learned that the width for a circular aperture, for single slit, you know, well, circular aperture, we learned that the width is 2.44 lambda L over D, where D is the diameter of the circular aperture, okay? So, what we want to do is we want to compare this to this, right? Okay, so what we're going to do, so we want this diameter to be equal to that diameter, right? If the light is within this diameter, ray model. If the light is greater than this diameter, wave model. Simple as that. Okay, so what we're going to do then, we're going to say that this, we're going to solve for the critical diameter, you know, right at the spot where if it's greater than, it's the wave, less than or equal to, it's the ray. So we're going to call this diameter DC, D critical, right? D critical. Okay, so we're going to say this, which is this, right? That's this here, equals just this, right? So the C stands for critical, all right? So this is the width of the single slit diffraction, and this is just the diameter of the hole. Okay? All right, now, okay, let's do it. So we have 2.44 lambda L equals dc squared. So D, the critical diameter, is just 2.44 lambda L square root. All right, well, what's that? Okay, so we're just going to make this makes, let's say we're just doing this experiment in the lab, right? So, you know, typical, and this is just, we're not being super exact, but pretty good. So we have 2.44. And let's just say that a typical wavelength of light is 500 nanometers, and that's true. So, you know, 500 something nanometers. You know, it could be 520, 510, whatever, just 500 nanometers. And then let's say, we're doing this in a lab, so we have like optical benches and things like that. So, the distance between here and here, a meter, something like that, a meter or so. Let's just put a meter. So if you do that, you get, all right, if you actually do that, you get 0.0011 meter. And that's basically the same as 1.1 millimeter, right? 1.1 millimeter. Okay, so what does that say? That says, choosing a model of light. Okay, when light passes through openings less than a millimeter, it's going to bend, right? So diffraction effects are important. Use the wave model of light. On the other hand, when light passes through openings greater than a millimeter, diffraction effects are small, are usually not important, so use the ray model. There you go. All right, that's really all there is to it. Now, how about if it's a millimeter? Well, then it depends how picky you are, all right? But anyway, that's useful information right there. All right, let's review. All right, so we learned about the ray model of light. Go straight and everything else, all right? Law of reflection, image formation in plane mirrors, law of refraction, total internal reflection, fiber optics, how to find images with lenses, graphical and mathematical, same thing with mirrors, and yeah, we said that. Okay, so just quickly review. So law of reflection, angle incident equals angles of reflection, always relative to the normal. Refraction, Snell's law, n1 sine theta 1 equals n2 sine theta 2, all right? Where the n1 is the medium where the source of light is, right? So here the source of light is in the air, so air is n1. And here the source of light's in the water, so the water is the n1. Got to be careful about little things like that can kill you. And here, if we're going from small n to large n, we bend toward the normal. Here, if we go from large to small, we bend away from the normal. And again, you don't have to memorize that. It's all in the equation. Okay, then this is the whole thing about apparent depth and real depth, right? The object is really here, but since we're out here, we would think it's really here. That's where we would see the image. And there's that formula. And again, you have to be careful. It's n1 and n2. And then this incredibly important thing in technology, if the angle is greater than this critical angle, there's nothing that's going to go outside, the wire, the cable or whatnot. It's just going to keep on reflecting. That's why it's called total internal reflection. All right, and we came up with the formula for that as well, just using Snell's law, nothing special. Okay, then we talked about lenses. So we're always going to assume parallel rays are coming in, which is a very good approximation. So lens, if they converge, that's the focal point, converging lens, positive focal point. If they diverge, it must be a diverging lens, right? Negative focal point. These three important rays, parallel in, focal out, focal in, parallel out, just straight through. Positive focal length. I goofed up there too. It's negative. Diverging lens, negative focal length. Right? Same three rays, parallel in, focal in, parallel out, just go straight. Then there's our wonderful equation, which is used for lenses and mirrors, but you got to keep this, when you're doing your homework, keep this handy and make sure you agree with this, all right? Because that's really crucial. And then concave mirror, so parallel in, then it reflects, converges to have a focal point. So for a concave mirror, the focal point's on the left. And again, some people call it converging mirror. And for a convex mirror or diverging mirror, the focal point's on the right? Because the parallel comes in and it diverges. And so you backtrack and you get the focal point. And then for concave mirror, you have your four rays, parallel in, focal in, parallel out. Center, which is twice the focal length, just backtracks on itself, or reflects back on itself, that's better. And then this guy's always wonderful. This angle equals that angle. That's concave. For convex, it's not so bad. So parallel in, it diverges, but focal out. Number 2 is focal in, but then it reflects here, so it's parallel out. Number 3 is a nice guy, just goes to the center, reflects back on itself. And then number 4, the good guy, just in, out, this angle equals that angle. And then there's the math. You have to be familiar with this stuff, though. So I used to always have this in front of my face when I did the homework, right, when I was in college, you know. Just have this in front of your face and you don't get it wrong. Then last but not least, when light passes through openings less than about 1 millimeter, you've got to worry about the spreading. You have to worry about diffraction. When light passes through openings bigger than 1 millimeter, diffraction is negligible, so it's a ray. And that is it. Thank you very much. Okay, we're done.